Good morning everyone. Let us start with the new session of computational process design on mass and energy balance. So in the last session we have looked at uh, preliminary flow sheet synthesis. So in that primarily we have looked at the hierarchical method given by Douglas. So in the hierarchical method what we do is we first design the flow sheet based on the stoichiometric reactions given, and based on that we calculate the profitability, and thereafter we start adding additional constants. So with the additional constant this profitability starts decreasing, and whenever for a particular option we find that the design becomes infeasible, we omit that particular design and we go ahead with only the feasible designs. So in order to continue along the same line, you can see that mass and energy balance are included in the process flowsheet design, just to find out whether a particular design is giving a reasonable profitability or not. So in this particular lesson what we are going to look at is how the linear mass and energy balance equations can be used here to obtain the reasonable design of the process flow sheet, and whether that design is giving the profitability or not. Based on that the design will be selected, and later on the detailed mass and energy balance will be performed. So just to start with here, mass and energy balances. So mass and energy balances are the fundamental tools. These are the fundamental tools for evaluating. These are the fundamental tools for evaluating the behavior of chemical process flow sheets. So again, these balance provide the essential insights into the distribution of the mass and energy within the process, and that helps in identification of the key parameters and performance indicators. Then the systematic application of mass and energy balance also enables the assessment of the process efficiency. It also gives the information about the material utilization and the energy conservation within the flow sheet. These are the important information when we are looking at the profitability of the given process flow sheet. So mass and energy balance, actually these are the steps which comes before the plant equipment sizing and economic evaluation. So clearly mass and energy balance is extremely important. It's a critical initial step in the design and the analysis of the chemical processes. Again, just to define mass balance is nothing but the uh, how the total mass of the system remains constant. Based on that we are trying to make a balance of different input streams and output streams, and based on that we check whether the total mass of the system remains constant or not. So clearly, unless the reaction is a nuclear reaction, a fundamental principle in chemical engineering which states that the total mass of the system remains constant regardless of any physical or chemical changes. Similarly, energy balance states that the total energy of the system remains constant regardless of the physical or chemical changes that may occur. Again, if we look at the mass balance or material balance equations, so material balance equations are nothing but mathematical expressions that describes the conservation of mass in the process. Again, these are typically expressed in terms of the input and output streams. Similarly, in energy balance, these are nothing but the mathematical expressions that describes the conservation of energy in a process, and typically these are expressed in terms of the heat transfer work and changes in the potential and kinetic energy. So if we look at the flow sheet model which we have seen in the last session, it involves typically three types of equations. So first class is the equations of connectivity. So when we are saying the equations of connectivity, these are nothing but the equations which are used for connecting different units. So for instance, the output of the one unit is given as an input to the next unit. So how this connection is done, that is described using these equations. The next class of equations are the specific equations for each unit. So these are nothing but mass and energy balance and equilibrium relations with respect to particular equipment. So how the input and output of a particular equipment or particular unit are related with each other, how the physical changes are taking place, all those are described using mass, energy and equilibrium relations, and these are referred as unit specific equations. And the third class is for equations with respect to physical properties. So how we can calculate different physical properties like enthalpies, equilibrium constants, and other transport and kinetic properties. These equations are referred as physical properties equations. So these are the three different classes of equations which we see when we are designing the flow sheet. So how to solve these equations? So in order to solve these equations, there are two methods by which people solve these equations. There are two approaches. The first approach is a modular approach. So in a modular approach, what we do is, each of these class of equations which I have described, they are considered as one module. Okay, and each of these modules are solved separately. So in this particular case, what we do is, first we make a module of physical property equations, then the second module is with respect to the equations corresponding to specific units, and the third type of module is a equations with respect to the connectivity of the units. So we solve each of these module one by one, one after each other. So first we solve the property equations, then we solve the equations with respect to each unit, and finally we look at the equations for connecting different units. So this is what we do in a modular approach. So clearly modular approach is easier because you are solving a subset of the problem at a time, and also the unit specific information can be incorporated in the modular approach much more easily. However, you can see that in a modular approach we require the input for each of these modules. So inputs has to be clearly specified. So again, very often what happens is, when we solve the entire chain of modules, we see that there is a discrepancy between the output of one unit and the input of the another unit. So in order to reconcile these discrepancies, very often there is a information recycling is there. So whenever information recycling is there, we require iterative procedure to solve these modules. Also, in some cases there are recycling streams present in the problem. In such cases also, there is a iterative procedure is required for solving the modular approach. In contrast with this, the another approach which we are talking about is a equation oriented approach. So in a equation oriented approach, what we do is we collect all the equations into a large set. So all these equations with respect to connectivity of unit, unit specific equations, and even the equations with respect to properties, all these equations are collected in a large set, and this entire set is then solved using some specific algorithms, which could be the algorithms like Newton's method. So clearly this second approach is more efficient, because now you are looking at all the equations together, and therefore using this approach we can get a more efficient solution. More efficient solution can be obtained. But the drawback of this approach is it is more cumbersome, because all the set of equations you are solving together, so it can be at a time it can be computationally challenging also. And again, incorporating the specific knowledge of the units is easy in the modular approach compared to the equation oriented approach. So these are pros and cons of both these approaches. So again, remember, in this case we wanted to solve the entire set of equations present in the preliminary flow sheet. So in order to solve these equations, we wanted to formulate the set of only linear equations. Why? Because we wanted to get the approximate values of the outputs, so that we can make the decision whether that particular flow sheet is good or bad. So in this case, the objective is to get a linear set of equations which we can solve easily. Once this preliminary analysis is done and the design is approved, then the detailed mass and energy balance is performed, where the actual non-linear equations are used. But here the objective is to formulate linear set of equations. So in order to get the linear set of equations, several assumptions are used. Typically, the assumption used in getting this linear equation is, we assume that the vapor and the liquid both are present at a saturated condition. So with this assumption, typically, the pressure and temperature is, we can set the pressure and temperature by using the equilibrium relations. So that simplifies our analysis significantly. So to solve the overall flow sheet, it is important to fix the temperature and pressure, and the strategy here is to obtain the linear set of equations. So for that, the different steps are given. So first step is fix the reasonable starting values of temperature and pressure of all process streams. So first we fix the temperature and pressure uh, for all the process streams. Then to obtain the outlet molar flows linearly related to inlet molar flows in each unit, approximate each unit with split fraction. So what we are trying to say here is, we wanted to represent the output from the unit, which should be proportional to the input, and for that we are using this fraction. We are using here the split fractions. So split fractions multiplied to a input that directly gives the molar flow rate of the output. Okay, so in this manner we can represent the output linearly with respect to the input. The third step is, all this set of linear equations which we have obtained for all the units, we solve these linear equations simultaneously for the overall mass balance. Once this overall mass balance is done, then we recalculate. The next step is, we recalculate the steam temperature, stream temperature and pressures using the equilibrium relations, and then we cross check these obtained temperature and pressures by using equilibrium relations are matching with the temperature and the pressures which we have assumed initially. If the temperature and pressure which we have assumed initially are matching with these recalculated temperatures and pressures from the equilibrium relations, in that case we directly go to the step 6, where after the mass balance with all temperatures and pressures, we perform the energy balance and evaluate the heat duties. But let's say these temperatures and pressures obtained using the equilibrium relationships are not same as the assumed values of temperatures and pressures. In that case, we again go back to the step 1, and we assume the new values of temperature and pressure, and we do this entire procedure iteratively till we matches the assumed temperature and pressure and the obtained temperature and pressure by using the equilibrium relations. So clearly in this case, saturated vapor and liquid streams are assumed. That enables calculating the physical properties easily. So clearly linear mass balance is a simple and fast method, because we are only formulating linear equations. Linear equations can be solved efficiently by using the methods like simplex algorithm, and we can evaluate the mass and energy balance for the candidate flow sheet approximately. The method involves creating block diagram for the mass balance, considering each unit in the flow sheet separately. So you can see that input and output of each unit we are now representing by using specific equations. So it enables the formulating the block diagram, and that helps in combining everything. The linear equations are set up for each unit and the mass balance is completed for all components. If necessary, the pressure and temperature may need to be readjusted and the procedure is repeated. As I said, we perform the mass and energy balance, we recalculate temperature and pressures by using the equilibrium relations, and if these are not matching, then we do this entire procedure repeatedly till the assumed values of temperature and pressures and the obtained values of temperature and pressures are matching with each other. The values obtained from the linear mass balance algorithm are only approximate due to ideal assumptions, but they provide a qualitative description of the relevant flow rates, temperatures, pressures and heat content. As I said, this entire methodology is easy to solve, but it gives only the approximate solution, and that is good enough to evaluate the candidate flow sheet. So in order to understand this concept, let's look at the mass balance equations for different units. We will start with the unit mixture, then we will move to splitter, reactor, flash unit, then to distillation column, absorber, stripper, and we wanted to first write down the mass balance equations for these, and this concept then we are going to use for solving the same ethanol flow sheets which we have seen earlier. This is the same flow sheet which we have seen in the first session. So in this particular flow sheet you can see that water, ethylene and recycled stream is mixed in the mixture, and this entire mixture is then charged to the reactor, and the reacted stream is then sent to the flash unit. In the flash unit, the vapor and the liquid is separated. So this vapor coming out from the flash unit is again sent to the absorber unit, where the ethanol is absorbed by the water. So this absorbed water with ethanol and other components are then again sent back to the mixture, where the liquid stream from the flash and the water rich stream coming from the absorber is also mixed, and this mixed stream then charged to the uh, first distillation column, where crotonaldehyde and the waste water is separated. The top product is then charged to the second distillation column, where diethyl ether is separated, and this separated diethyl ether is then charged to the mixture unit, primarily because that reduces the conversion of the side reaction, it suppresses the side reaction, and the bottom product coming from the second distillation column is then given to the third distillation column, where ethanol product is separated and the wastewater is removed in the bottom. So this is the flow sheet. With respect to this flow sheet, all these equipments, all these units, we are going to look at their mass balances, and the entire mass balance of this ethanol flow sheet we are going to look at towards the end. So let's start with the first unit. In the mixer unit, if you look at the mixer unit, typically the mixer unit is like this, where multiple inputs are coming in, and all these inputs are combined, and finally one output is going. So mixer unit actually sums up all the inlet streams as a single output stream. So given upstream unit, let's say there are upstream units I1, I2, that fed to the mixture with the J1 outlet from the unit 1, and J2 outlet from the unit uh, I2 for component K. Then the outlet from the mixture for the kth component, molar flow rate of the kth component coming out from the mixture can be given by using this equation. So here you can see that mu, this notation mu actually refers to the molar flow rate. Here superscript K represents the component K, whereas the subscript M actually represents the unit. So here mu Km is nothing but the molar flow rate of the kth component coming out from the mixture. So you can see that that is the summation of the molar flow rate of uh, component K for J1 outlet and J2 outlet from the unit I1 and I2, which are the upstream units. So you can see that in this case, if I have to write down the UMK, UMK is nothing but in this case will be the summation of all these three molar flow rates. So this is the model equation for the mixture unit. So you can clearly see that this model equation is linear in nature, linear in nature. So now let's look at the second unit. Second unit is a splitter unit. So splitter unit, as the name itself suggests, it divides the feed stream into specified fractions zeta j for each output stream j. So this fraction zeta j is very important here. So whatever is the input is there, that input is multiplied to the corresponding fraction, and that gives the output stream j. So you can see that unlike the mixture, here in the splitter, the inlet stream is splitted into multiple outlet streams. And if you look at the mass balance here, so the outlet from the each of these streams, J streams here can be represented by using this equation. So you can see that mu Sj K, this is nothing but molar flow rate of jth stream for the component K coming out from the splitter, and that should be equals to zeta j, where zeta j is nothing but the split fraction. So zeta j multiplied by mu I n k. So here mu I n k is nothing but the molar flow rate of the input for the kth component, that multiplied by the corresponding split fraction, and that gives you the molar flow rate of the outlet stream J. So here you can see that there are total ns number of outlet streams are there, output streams are there. So we can write this balance equation only for 1 to all the way to ns minus 1, and for the last stream, ns stream, we have to write down the another equation which is nothing but mu s k ns. So this is nothing but the molar flow rate of the kth component coming out from the ns stream in the ns stream of the uh, splitter, and that is obtained as 1 minus summation of zeta j. This summation is going from j equals to 1 to ns minus 1 into mu I n k. So you can see that the summation of this zeta j from 1 to ns will give you equals to 1. So clearly for the last stream, the zeta j value is not required, only the zeta j value up to ns minus 1 streams are required, and for the last stream the zeta j value is nothing but 1 minus summation of all the zeta j's up to ns minus 1 streams. So with these two equations we can solve the mass balance for the splitter. Again, both these equations are linear in nature. So coming back to a third unit is a reactor unit. So in a reactor unit, what we are doing is we are looking at molar conversion of inlet streams into product stream with fixed conversion is considered here. So in this case, what we are trying to do is we are trying to represent inlet and outlet in terms of the molar flow rate, and instead of the mole fraction. So you can see that by representing input output in terms of molar flow rate has the advantage in the sense that that will give you the linear equations. So in this case, for each reaction R, the limiting component, let's say, is LR, and the normalized stoichiometric coefficients are gamma RK. Gamma RK can be given as CRK divided by CRLR. So here this is nothing but the stoichiometric coefficient of the kth component in R reaction divided by stoichiometric coefficient of the limiting component LR in the Rth reaction, that gives us the gamma RK. Once we calculate the gamma RK for all the components, we can write down the mass balance. So in this case, you can see that this normalized stoichiometric coefficient gamma RK is very interesting factor here. You can see that the gamma RK it is greater than 0 when the component K is a product, whereas gamma RK is less than 0 when the component is a reactant, whereas when the component is inert, in that case gamma RK is equals to 0. So now with this information we can write down the mass balance. So the mass balance in this case can be written as mu RK. Mu RK is nothing but the molar flow rate of kth component coming out from the reactor R. It is given as mu I n k. So it is nothing but the molar flow rate of the kth component in the input plus summation of R equals to 1 to nr. So we are doing the summation from reaction 1 to all nr reaction, and we are trying to see whether the component K is produced or consumed in different reactions. So that is accounted through this summation. So here you can see that this summation is nothing but what? It is nothing but summation of gamma RK into nr into mu I n lr. So here you can see that gamma RK is nothing but the normalized stoichiometric coefficient of the kth component in R reaction. Eta R is nothing but the conversion. This is nothing but the conversion of limiting component in the Rth reaction, and mu I n is nothing but the inlet molar flow rate of the limiting component. Okay, so this particular equation enables writing the mass balance for input and output of the reactor in a linear fashion, and we will illustrate that using a simple example. So consider a very simple example here. So there are two reactions occurring. First reaction is methane is reacting with oxygen to produce CO2 plus 2H2O, and the conversion here is 0.7. The second reaction is C2H6 is reacting with oxygen, that is producing uh, uh, carbon dioxide and water. Again here the conversion is 0.9. So in this case we wanted to write down the material balance. So again, since there are two reactions are there with respect to all the components, their coefficients, stoichiometric coefficients are written. So you can see that the CH4, it is the reactant in the reaction 1, so that is why its stoichiometric coefficient is taken as -1. Oxygen is a reactant, and that is why its stoichiometric coefficient is taken as -2. CO2 is getting produced here in the second reaction, so its stoichiometric coefficient is 1. H2O is also getting produced, so that's why its stoichiometric coefficient is taken as 2. Again, in the first reaction, C2H6 is not getting produced or consumed, so that is why its stoichiometric coefficient is taken as 0. Now corresponding to the second reaction, in the second reaction C2H6, there is no CH4 in the second reaction, so its corresponding stoichiometric coefficient is 0. Then oxygen O2 is getting consumed here, so 7 by 2 is the stoichiometric coefficient, so that is represented as -7 by 2, since this is as a used as a reactant. Then C2H6 is also getting consumed, so its stoichiometric coefficient is -1. CO2 is getting produced, so its stoichiometric coefficient is 2, and water is getting produced, so its stoichiometric coefficient is 3. Now with these uh, uh, values, now we can write down the uh, mass balance here, material balance. So we can write down the mass balance with respect to each of these components. So mu r CH4 is nothing but the mass balance of the methane. So mu r CH4 will be given as mu I n CH4 by using this equation, and then we are trying to see the methane is getting consumed or produced uh, in different reactions or not. So in this case you can see that, so it is getting consumed, so that becomes mu I n CH4, and the conversion is 0.7, so minus 0.7 mu I n CH4. So that is what we have obtained. So with this the value of mu r CH4 obtained is 0.3 mu I n CH4. Similarly, for C2H6, mu r C2H6 is mu in C2H6 minus C2H6, which is getting consumed by second reaction with a conversion of 0.9. So that is 0.9 into mu I n C2H6. So that becomes 0.1 mu I n C2H6. And for the other component also we can write down the mass balance here. So mu r O2 is nothing but the mass balance for the oxygen. So you can see that the oxygen is getting consumed in reaction 1 as well as reaction 2. So mu r O2 coming out from the reactor will be equals to mu r in, which is nothing but the input to the reactor, minus this 2 is the stoichiometric coefficient, -2 is coming because oxygen is getting consumed, multiplied by first reaction has a conversion of 0.7, so 0.7 mu I n, and in this case it has to be represented, mu I n has to be represented in terms of the limiting component. So in the first reaction the limiting component is CH4, so that is why it is -2 into 0.7 mu I n CH4. Similarly, in the second reaction it will be -7 by 2 into 0.9, which is the conversion, into mu I n C2H6, because in the second reaction the limiting component is C2H6. In a similar manner, for the water, the mass balance, material balance can be written here as mu r H2O is nothing but the amount of molar flow rate of the water coming out from the reactor, that will be equals to molar flow rate of the water coming in the reactor, plus water is getting produced in the first reaction, so that becomes 2 into 0.7 mu ion CH4. Again it is getting produced in the second reaction, so that becomes 3 into 0.9 mu ion C2H6. And the last component balance is for CO2. So mu r CO2 is nothing but the molar flow rate of CO2 coming out from the reactor will be given as mu ion CO2, that is nothing but the molar flow rate of the CO2 coming in the reactor, plus CO2 is getting produced in the first reaction, so that becomes 0.7 into mu ion CH4 plus 2 into 0.9 into mu ion C2H6. You can see that in these three reactions, you can see that the consumption or production of O2, H2 and CO2, these are represented in terms of the limiting reactants. So again you can see that all these equations are linear in nature. These are linear. These are linear in nature. So we can solve these equations easily. Now coming back to another unit, a flash unit is a extremely important unit. This particular unit is extremely important primarily because it serves as a building block in all the stage separation operations like distillation and absorption. So each of the tray of the distillation column or the absorption tower is similar to the flash unit we are looking at. Okay, so in order to develop the model for flash unit, an overall split fraction is assumed. So overall split fraction zeta k is nothing but what? Zeta k is nothing but Vk divided by Fk. Here Vk is nothing but the molar flow rate of the kth component in vapor divided by Fk. Fk is nothing but the molar flow rate of the kth component in the feed. So Vk by Fk is going to give us the zeta k. So here the k is the component. Again there are total n components present, isn't it? Again let's assume that n is the key component, correct? And phi here is nothing but V by F. So V is nothing but the molar flow rate of the vapor divided by molar flow rate of the feed. So this includes all the components. So so in this particular case, the variables present in the problem are what? The variables present in the problem is zeta n. Zeta n is nothing but the split fraction in the vapor recovery for the key component n. Phi is nothing but the phi is the fraction V by F. P is the pressure and T is the temperature and Q is the heat supplied. The model equations we can write in this case. So for a material balance we will not be looking at Q right now, but all other variables are there. Using these variables we can write down the model equations. So model equations will be what? So feed molar flow rate of the kth component in the feed can be given as molar flow rate of the kth component in the liquid plus molar flow rate of the kth component in the vapor. So Fk is given as Lk plus Vk, where K is varying as 1 to total number of components n com. Again Vk divided by V is nothing but what? Vk divided by V is nothing but Yk, isn't it? That is nothing but the mole fraction present in the vapor, mole fraction of the kth component in the vapor, and that can be given by this equilibrium relation, which is nothing but K, capital K, which is a function of x, p and t. This is the Henry's law, multiplied by Lk by L. So here small Lk is nothing but the molar flow rate of the kth component in the liquid divided by total molar flow rate of the liquid. So this Lk by L is nothing but what? It is nothing but xk. It is nothing but the mole fraction of the kth component in the liquid. Again summation of all Lk will give you total molar flow rate of the liquid. Similarly summation of all Vk, which is nothing but the molar flow rate of the kth component, all components in the vapor, that should be equals to total molar flow rate of the vapor. Now if we look at this entire information in terms of the unit, it is like this. So the feed input to the flash unit is capital F, which is nothing but the molar flow rate of the feed. Zk is the mole fraction of the feed for the kth component. Fk is nothing but the molar flow rate of the kth component in the feed, and that is given as Fzk. Similarly, the top product which is coming out will be represented by this. So the total molar flow rate which is coming from the top is capital V, which is nothing but the vapor here. Remember, in the flash unit the top product is vapor, so V, capital V, is the total molar flow rate of the vapor coming out from the flash unit. The mole fraction of the kth component in the vapor V is given by Yk, and Vk is nothing but the molar flow rate of the kth component in the vapor, which is given as capital V into Yk. Similarly, for the bottom, in the bottom the product coming out from the flash unit will be liquid, so the total molar flow rate of the liquid coming out from the bottom is capital L. Xk is nothing but the mole fraction of mole fraction of the kth component in the liquid, and Lk is nothing but the molar flow rate of kth component in the liquid. So Lk is given as capital L into Xk. So this particular input output representation we wanted to represent in a simpler way, like if there is a input mu I and k to the flash unit, we wanted to represent what will be the molar flow rate which is coming out as a top product and what will be the molar flow rate which is coming out as a bottom product, and this we wanted to represent in terms of the split fraction. So that we will get a linear equations in terms of input and output. That is what the ultimate objective is. Now here the additional complications comes because since this particular unit is a equilibrium unit where the amount of vapor and the liquid coming out from the top and bottom depends on the equilibrium relations present between the vapor and liquid. So clearly equilibrium relations has to be satisfied, and in order to make sure that the equilibrium relations are satisfied, some mathematical recalculations are done in order to make sure that whatever the values we are getting are consistent. So remember, in this case we start with the assumption of a split fraction, but that split fraction assumption is actually satisfying the equilibrium relation or not, that we have to check all the time. So there we require some trial and error. So that part we are going to look at in the next slide. So clearly you can see that if we see the total number of variables here, total number of variables if we see, so 1, 2, then 3, then 4, 5 and 6. So there are total 6 variables are there, and number of equations are 1, 2, 3 and 4. There are 4 equations and 6 variables are there. Total number of variables are 6, number of equations are 4. So in this case clearly the degree of freedom is 2. So what it means is, by specifying 2 variables we can define the system completely. That is what it means. So now there are different ways in which we can select 2 variables here, isn't it? So based on that there are 3 cases. So case 1 is nothing but what? Case 1 is we can fix the zeta n. Zeta n is nothing but the split fraction for the split fraction in the vapor recoveries. Remember, here zeta is the split fraction with respect to the vapor recovery. So split fraction in the vapor recovery for the key component n is given, and out of the remaining 2 variables, temperature and pressure, any one of them we are going to specify. So even if we specify one of these 2 and zeta n, then the system is completely specified and we will get a unique solution. Similarly, the another case could be we can specify temperature and pressure, isn't it? So with that also we can calculate, we can get the unique solution. The third case is phi is specified, and out of t and p one of these is specified. So these are the 3 cases which are used in order to reconcile the assumed values of split fractions with the equilibrium relations those are present with respect to the flash unit. So those back calculations we are going to do. So for that different equations are derived here. So in this case the approximate vapor liquid equilibrium equations used for low and moderate pressures are given by this. This is the equation. So phi k yk capital P is equals to gamma k xk fk naught. So here phi k gamma k and fk naught are nothing but the fugacity coefficient. So this is a fugacity coefficient for the vapor. uh, Gamma k is the activity coefficient of the liquid, and fk naught is nothing but the fugacity of the pure component. So we can write down this equation for all n components, isn't it? Now uh, at equilibrium the equation which is valid at equilibrium is this Henry's law equation, which is nothing but yk is given as uh, kk xk. So we can find out kk is nothing but the equilibrium constant, which can be given as yk divided by xk, and yk divided by xk we can find out from this equation number 1. So that yk divided by xk is nothing but what, gamma k fk naught divided by phi k by p. So that is what is written here. So you can see that the equation 2 is derived from equation 1 and this equation. Again, for an ideal behavior, we assume that the fugacity of the vapor is equals to 1. Again, the activity coefficient of the kth component in the liquid is equals to 1, and also the fugacity of the pure component fk naught is equals to the pressure, which is nothing but the vapor pressure here. So pk naught. Okay, so this pk naught also we can calculate by using Antoine equations. So this Antoine equation we can use for calculating the pk naught. So pk naught can be given as ln pk naught is equals to ak minus bk divided by t plus ck. Here a, b and c, these are nothing but the coefficients, empirical coefficients for Antoine equation. Now we can use these ideal equations, ideal relationships in equation number 1. So with that, this phi k becomes 1, this gamma k becomes 1, and this fk naught becomes pk naught. So with that, the simplified equation obtained is this. Now this simplified equation we can rearrange. So yk by xk can be obtained as pk naught divided by p. So this is nothing but vapor pressure of kth component divided by the total pressure, that gives us the kk. So this equilibrium constant kk can be obtained as pk naught by p. So this particular equation is nothing but what? This particular equation is nothing but the Raoult's law, isn't it? So mole fraction of the kth component in the vapor multiplied by uh, uh, pressure, saturation pressure, is equals to xk, which is nothing but the mole fraction of the kth component in the liquid multiplied by vapor pressure, isn't it? So so yk into total pressure is given as xk into vapor pressure pk naught. That is what the Raoult's law is. Now we can obtain the relative volatility here, relative volatility of the component k with respect to the key component n. Now why relative volatility? We have to derive all these equations in terms of relative volatility, primarily because this relative volatility is relatively independent of p, and it is less sensitive to t than kk. That is why we are trying to modify all these equations in terms of the relative volatility. Now definition of relative volatility is what? Definition of relative volatility is the mole fraction of yk, kth component in the vapor, divided by mole fraction of kth component in the liquid, divided by mole fraction of key component in vapor divided by mole fraction of key component in the liquid. So this ratio is nothing but relative volatility of component k with respect to the key component n. So yk by xk is nothing but kk. That is what we have derived here in the equation number 4. So kk divided by kn, that gives us the alpha kn, which is nothing but the relative volatility of the component k with respect to the key component n. So this is given as pk naught divided by pn naught, isn't it? So you can clearly see that pk naught and pn naught, these both can be calculated by using Antoine equation, and we can calculate the relative volatility. So in this case, again, this relative volatility we can represent in terms of the molar flow rate of the vapor and the molar flow rate of the liquid with respect to the component k and with respect to the key component. So in this case, you can see that alpha kn is given by what? Yk xk divided by yn xn. Now this entire equation we can multiply and divide by these two terms. It doesn't matter because these are going to get cancelled out, isn't it? But yk into v will be nothing but what? Yk into v is nothing but vk. Similarly, xk into l is nothing but what? Lk. Also yn into v will be nothing but vn, and xn into l will be ln. So we have now represented this alpha kn, which is nothing but the relative volatility of component k with respect to the key component n in terms of the molar flow rate of component k in the vapor and liquid, and the molar flow rate of the key component n in vapor and liquid. That is what we have obtained in equation number 5. Now once we have obtained this equation number 5, this can be further simplified. This can be further simplified in the sense that what will be Vk? Remember, Vk we have defined as Vk is nothing but what? Vk is nothing but zeta k into fk. That is what we are saying. Zeta k is nothing but the split fraction. So how much split fraction is going to happen with respect to the feed molar flow rate of the component k in the feed? That is represented by using this equation, isn't it? So Vk is given as zeta k into Fk. Similarly, Lk is given by 1 minus zeta k into Fk. Now I can obtain Vk divided by Lk directly. So that is nothing but what? Zeta k divided by 1 minus zeta k. So I can remove this by using that, isn't it? So now from equation 4, this is the equation we have obtained from equation number 4. Yk by xk is given as kk, isn't it? Yk by xk is given as kk. Now yk by xk we can multiply and divide by this v by l. So v by l into l by v. So these two factors are going to get cancelled out with each other. It doesn't matter, isn't it? So we are multiplying and dividing the same factor here. So yk into v becomes vk, and xk into l becomes lk. So this becomes vk by lk into l by v. And Vk by Lk is nothing but what? Zeta k divided by 1 minus zeta k. So in this, by putting that, Kk is obtained as this, zeta k into capital L divided by V into 1 minus zeta k. This is what the expression we have obtained for the Kk. Now similar to that, we can rearrange the equation for alpha kn. Alpha kn is the relative volatility. Here relative volatility is given by what? Vk divided by Lk divided by Vn by Ln. So now Vk by Lk is zeta k divided by 1 minus zeta k, and Vn by Ln is nothing but what? Zeta n divided by 1 minus zeta n. We can rearrange this equation and obtain the expression of zeta k. So zeta k is given by alpha kn into zeta n divided by 1 plus alpha kn minus 1 into zeta n. Now this particular equation is very important. This particular equation is very important primarily because this enables calculating the split fraction for the remaining k components if you know the split fraction for key component. So if you know the split fraction for the key component, we can calculate the split fraction for any component which is present in the mixture, provided that we know the corresponding relative volatilities. So now for non-volatile component, clearly the relative volatility tends to 0, and zeta k split fraction is 0, isn't it? Because it's not going to represent in the vapor phase. For non-condensable component, everything will be in the vapor. So clearly you can see that the relative volatility tends to infinity, whereas zeta k is equals to 1. So in addition to zeta k, clearly you can see that now we have got all the equations, how zeta k, how pressure and how temperature are related in the equilibrium relationships. Those we have derived in this case. Now we wanted to see how we can fix any two of these and back calculate the other and see whether it is matching with the assumed value of zeta k, t or p is matching with that or not. So for that, again we are using the bubble point or dew point calculations. Okay. So in this case, at the bubble point, clearly yi, which is nothing but the mole fraction of the components in the vapor phase, their summation should be equals to 1, and also this is from the Henry's law, isn't it? So that yi is given by what? Ki into xi. So again this summation ki by ki into xi will also be equals to 1. So this is the equation we have obtained. Summation of ki xi is equals to 1. Now this entire equation we can divide by Kn. We can divide this entire equation by Kn. So if I divide this entire equation by Kn, the right hand side will be what? 1 by Kn. So that is what is represented 1 by Kn. And this Ki divided by Kn will be represented into Xi in the summation. So this Ki by Kn is what? Ki by Kn is the relative volatility. So that is what we have written, relative volatility of the component I with respect to key component N. So in this case 1 by Kn is nothing but what? This entire summation represents what? This is nothing but the average relative volatility, isn't it? We are summing up, we are finding out the average relative volatility with respect to the mole fractions, isn't it? So this is nothing but the alpha bar, isn't it? So this is the average relative volatility. So 1 by Kn is equals to average relative volatility. Now remember in the previous slide you can see that alpha Kn is given by what? Alpha Kn is given by Pk by Pn, isn't it? So the same expression we have used here. So you can see that the Kk is divided by Pk naught by P. So this is the equation number 4. We can go back and see in equation number 4. Just wait. So see, this is the equation number 4. You can see Kk is given as Pk naught by P. This is nothing but the ratio of vapor pressure divided by total pressure, isn't it? So the same expression is used here. So Pk by P is Kk, correct? Pk by P is Kk. So again, this is nothing but what? This is Kk by Kn is nothing but alpha Kn. So I can represent this Kk as Kn into alpha Kn, isn't it? Isn't it? So remember Kk by Kn is nothing but alpha Kn. So this particular equation I can represent and I can calculate Kk as Kn into alpha Kn. So that is what is written here, isn't it? But this Kn is nothing but what? Kn is nothing but 1 by alpha. So I can put this Kn as 1 by alpha. So Kk can be calculated in terms of the relative volatility of the component K with respect to the key component N divided by average relative volatility. So ratio of the relative volatility and average relative volatility gives us the constant Kk. Okay, so now once we got this equation 10, now we are now we can interchangeably find out pressure, temperature and the split fraction here. So here let's say if the T is fixed and P is unknown, remember the zeta is, let's say zeta is fixed, and once the zeta is fixed, then in that case either T has to be fixed or P has to be fixed. So let's say T is fixed and P is unknown. In that case we can back calculate the P. We can back calculate the P by using this particular equation. Remember in this case we can back calculate P. So P will be nothing but what? Pk naught into alpha bar divided by alpha Kn. So we can back calculate the P and check whether the assumed value of P is matching with this P or not. When P is known and T is unknown, in that case what we can do, we can calculate the vapor pressure Pk. We can calculate the vapor pressure Pk naught as P into this entire thing, P into this, isn't it? So this equation will give me the vapor pressure, and we can use the Antoine equation here and find out what temperature is going to satisfy this particular vapor pressure, and in that way we can back calculate T. So clearly if the P is unknown, we can assume the starting value of P and then we can back calculate the P using this equilibrium relation, and we can check whether that P is satisfying or not. Similarly, when T is assumed, we can back calculate the T using this particular equation, and we can check the assumed value of T and the obtained value of T using the equilibrium relations are matching or not. Okay. So again clearly all these equations are based on what? These are based on the Henry's law, isn't it? So that is why in order to minimize the approximation error, the index K is selected to be most abundant component in the liquid phase. So that is going to minimize the errors. Okay. Now with using this discussion, now there are three methods to reconcile the flash unit calculations. So case one is case 1 is when zeta n is fixed, and out of p or t 1 is specified. So in that case what we can do is, for a fixed zeta n and let's say p is fixed, in that case we can guess the suitable value of temperature T. Or if the T is fixed, in that case we are going to guess the suitable value of P, and then we are going to calculate Kn and alpha Kn. So Kn is the equilibrium constant here, and alpha Kn is nothing but the relative volatility of the kth component with respect to the key component n. So we can calculate Kn and alpha Kn at a given T. Then we can calculate zeta k using this particular equation. Remember I said that once we know zeta n, this zeta n can be used to calculate the split fraction for the other components, isn't it? So zeta k we can calculate if we know zeta n using this formula. Once we know the zeta k for what are the split fraction for all the components, if we know that, we can perform the mass balance. So you can find out what will be the molar flow rate of the vapor. We can find out the mole fraction of the kth component in the vapor. We can also find out the molar flow rate of the kth component in the liquid, and also we can calculate uh, uh, xk. This is xk, this is xk. So we can calculate xk here. Xk is given as lk divided by summation of li. Then uh, then we can calculate, let's say in this case the T is we have guessed the value of T. So what we have to do is we can back calculate the P by using this equation, isn't it, and check whether this P is same as the started value of P. Again for the obtained value of this vapor pressure, we can use the Antoine equation and we can back calculate T, and we can check whether this obtained T is indeed near to the assumed suitable guess value of T or not. If it is not, then again we are going to repeat this procedure by making another guess. So this is what the case number 1. Remember, this entire procedure we are doing in order to fix zeta 1, zeta 2 all the way to zeta n, isn't it? Once we know the split fraction, then the input and output we can represent using the linear equation. So in this case, finding the zetas for different components is important, and these zetas should reconcile with the energy with the vapor liquid equilibrium relation. That is why this entire iterative procedure used in order to make sure that whatever the zeta values we are obtaining, these are indeed satisfying the vapor liquid equilibrium. Now in case 2, unlike the case 1, in case 2 P and T are specified, so zeta is unknown. So we can start with the suitable value of zeta n, isn't it, by assuming a key component n, isn't it? Then we can perform the step 1 2 3 4. All these 4 steps we can perform, and if the bubble point calculation, then we calculate the average relative volatility average relative volatility, and if this bubble point calculations are satisfying with the actual values, then we stop, else the new guess values for zeta n we have to select, and we have to do this entire procedure again. In case 3, phi is specified and either P or T is specified. So for fixed phi and P, we guess the suitable value of T. Again we calculate Kn, alpha Kn at the fixed value of T. Then we calculate theta. Here theta is defined as Kn phi divided by 1 minus phi, and that is equals to Vn by Ln. Again we can calculate zeta n as theta divided by 1 plus theta. So we can calculate the zeta n values from this, and if the bubble point calculations are satisfying the assumed values, then we stop, else we have to select the new value of P or T. Okay, so these are the 3 cases people use in order to make sure that whatever the split fractions you are calculating or assuming for the flash unit are indeed satisfying the vapor liquid equilibrium or not. So we will look at one problem with respect to case 1 in order to appreciate how it is done. So in this case there is a mixture of benzene, toluene and orthoxylene which has to be separated in a flash unit. Now in this case, toluene we have to consider as a key component, okay, and we wanted to perform the calculation for the fixed zeta n equals to 0.9. So we are assuming that the split fraction of the toluene from the feed to the vapor is 0.9, isn't it? And we are also starting with the fixed value of p, which is equals to 1 bar in this case. Now let us see the data. So in this case, the molar flow rate of the different components in the feed are given. So orthoxylene is equals to 40 kilomole per hour, toluene is 50 kilomole per hour, and benzene is 30 kilomole per hour. Also the boiling points of these three components are given. So orthoxylene has the boiling point of 418 Kelvin, toluene is 383 Kelvin, and benzene is 353 Kelvin. So clearly you can see that in the top product we will primarily have benzene and some amount of toluene. So since the toluene has the relative boiling point in between these two, we are trying to consider toluene as a key component here. Again, the vapor pressure for each of these components we can calculate by using Antoine equations. So these are the Antoine equations given, where P1 naught, P2 naught, P3 naught, these are the vapor pressure of component 1, component 2, component 3, and these are represented in mm of Hg, and here the temperature T is represented in Kelvin. So these are the three Antoine equations given. Now for case 1, remember in case 1 there is a zeta n which is fixed. That means the split fraction of the key component is fixed, which is equals to 0.9. The key component here is toluene, and the pressure is given as 1 bar. So clearly we have to assume the starting value of the temperature, isn't it? So temperature value let's assume as 390 Kelvin. So now at 390 Kelvin we can again use this Antoine equation and we can calculate P1, P2, P3, which comes out to be 339.69 mmHg for orthoxylene. For toluene it comes out to be 891.82 mm of Hg, and for benzene it comes out to be 2114.34 mm of Hg. So these are the vapor pressure we have obtained by using three Antoine equation. Now these three vapor pressure we can use to calculate the relative volatility. Remember, relative volatility alpha Kn is given by what? Pk naught divided by Pn naught, isn't it? That is what we have derived earlier. So Pk naught by Pn naught. So Pk naught in this case, let's say for the component 1 here, that becomes alpha 1 by 2, isn't it? So it is nothing but the relative volatility of the component 1 with respect to the key component toluene, isn't it? Remember here key component is component 2. So now we can calculate here relative volatility alpha Kn as P1 naught divided by P2 naught. So that comes out to be 0.380. Similarly, the relative volatility of the third component with respect to the key component 2 alpha 32 is obtained as 2.370. These are just the ratio of the vapor pressures obtained using the Antoine equation. So once we get the relative volatilities, these relative volatilities we have obtained for component 1 and component 2. So clearly the relative volatility of the component 2 with respect to 2 will be 1, isn't it? So now we can calculate the split fraction. Remember zeta k, I said that zeta k we can represent in terms of the split fraction of the key component. Remember zeta n value is given 0.9. So we can use this zeta n and alpha kn values we have calculated for all the components. We can back calculate zeta k. So zeta 1 comes out to be in this case is alpha 1 2 into zeta 2 divided by 1 plus alpha 1 2 minus 1 into uh, zeta 2. So with this we can calculate the zeta k, which comes out to be 0.774. So this is the split fraction of the first component, which is nothing but orthoxylene. Similarly, we can calculate the split fraction of the third component, which is nothing but benzene. So which comes out to be alpha 3 by 2 into zeta 2 divided by 1 plus alpha 3 by 2 minus 1 zeta 2. So this is nothing but 2.370, which we have already calculated, multiplied by zeta 2, which is nothing but the split fraction of the key component, which is 0.9, divided by 1 plus 2.370 minus 1 into 0.9. So that comes out to be 0.955. So now we know zeta k, we know zeta 1, we know zeta 3, and we also know zeta 2. Zeta 2 is 0.9. That is what we have assumed initially, isn't it? So now we know zeta 1, zeta 2, zeta 3. With these three zeta values, we can now perform the mass balance. So mass balance in this case, V1 will be what? V1 is nothing but the molar flow rate of the vapor, molar flow rate of the component 1 in the vapor. So that is nothing but what? F1 into split fraction. So F1 is 40, isn't it? That is what given in the table. See, F1 is given as 40. 40 into corresponding split fraction. So 0.774, that gives me 13.96. Correct. Now this is V1. So V1 plus L1 should be equals to F1. So we can calculate L1. So L1 is nothing but 40 minus 30.96. That comes out to be 9.04 kilomole per hour, isn't it? Similarly, V2. So F2 is nothing but what? F2 in this case is given as 50. You can see the F2 is given as 50. So we can use 50 into F2, which is nothing F2, which is nothing but 0.9. F2 is epsilon 2 is 0.9 and F2 is 50. So F2 into epsilon 2 zeta 2. F2 into zeta 2 is multiplied. That gives us 45, and the liquid here will be what? V2 plus L2 should be equals to F2. So we can calculate L2, and L2 comes out to be 50 minus V2. So that comes out to be 5 kilomole per hour. Similarly, V3 will be nothing but what? V3 will be nothing but F3 multiplied by zeta 3, and zeta 3 is 0.95. Right? So 30 into 0.955 is 28.65. So this is L3. This is L3. So L3 is given as 30 minus V3, that becomes 28.65. So it becomes 1.35. Now we have obtained L1, L2 and L3. So we can now calculate X1, X2, X3. So X1 will be nothing but what? L1 divided by summation of all these L1, L2, L3. So that is nothing but 9.04 divided by summation of all L1, L2, L3. That is comes out to be 0.587. So this is X1. Similarly, we can calculate X2, which is 0.324, and similarly we can calculate X3, which is 0.088. Once we have obtained X1, X2, X3, once we have obtained X1, X2, X3, now we can do the bubble point calculations. So remember here P1 which we have obtained by using Antoine equation is 339.69, isn't it? And this P1 should be equals to what? This P1 should be equals to alpha Kn by alpha bar into P. That is what we have derived earlier. If you go back and see, this is the same equation we have derived. So I will go back. So see, this is the equation we have derived, isn't it? See, so we can calculate the vapor pressure using this equation. Okay, so let us see what is the value. So you can see that this P1 value comes out to be, if I calculate alpha Kn by alpha, so see this P1 value which we have obtained from Antoine equation. This we have obtained from Antoine equation, and this we have obtained from equilibrium relation. So from equilibrium relation, the P1 value comes out to be 377.17. Remember, this is nothing but alpha Kn divided by average value of relative volatility. Average is calculated with respect to the mole fraction in the liquid. So Xi into alpha K, alpha In, that is what is the denominator here. So we get 377.17, which comes out to be P1, which is nothing but the relative, which is nothing but the vapor pressure. Now with respect to this vapor pressure, we can again go back to the Antoine equation. So this is the Antoine equation. This is the Antoine equation for the component 1, and for this component 1 we can again back calculate the temperature, and this back calculated temperature comes out to be 393.10 Kelvin, which is very close to the assumed value of 390. So clearly you can see that the split fractions which we have obtained, which is nothing but, these are the split fractions we have obtained. These split fractions with respect to vapor are indeed satisfying the equilibrium, because the temperature is more or less matching here. Okay, so this is how we have to reconcile the split fraction values with respect to the equilibrium relation, and we will again look at some more equipment like absorber and distillation column, and based on that we are again going to solve the entire uh, the flow sheet which we have discussed earlier. So this entire this entire flow sheet we are going to solve using these concepts. So idea here is to get the linear equations for each of these units and then solving all these linear equations simultaneously. Then we are going to solve these equations together by using some suitable solvers like simplex algorithm, etc. Okay, so thank you. We will continue from this point in the next class.